Howdy, this is your friendly neighborhood physics teacher here. So we have a test on Friday, and it's over energy and thermodynamics. I have the review here that you can see. Let me make it bigger so you can see it all. There we go. Okay, so here's the review. I'll go through the whole entire of the review. It is 30 questions, so this video might be a little lengthy. I do apologize about that, but I want to make sure I hit all the key points. And if it's really important, I'll definitely put a yellow star by it. So if you see a yellow star, that means pay attention to me. You need to pay attention to everything else, but it's like very important if it has a yellow star. So let's go through the review. Number 1, which of the following best describes the relationship between two systems in thermal equilibrium? So the key word here is thermal equilibrium. So equilibrium means equal. It's the same. So what happens when it's the same? So we have a couple of choices here. No energy is exchanged. The volumes are equal. Masses are equal. The velocity is 0. Now, thermal equilibrium. Thermal is energy. Equilibrium. So our answer is A, no energy is exchanged. Because if it's balanced, remember in the 0th law of thermodynamics, it states that everything wants to go to equilibrium. So if it's not in equilibrium, energy is going to transfer. But if it is, no more energy transfer. So there we go, question 1 down. Number 2, heat flow occurs between two bodies in thermal contact when they differ in which of the following properties? So basically breaking that down, when does heat flow occur? So again, going back to what happens for energy, because that's what heat is energy, for energy to transfer. And again, going back to that 0th law of thermodynamics, if there's a change in temperature, that you're going to have that energy transfer. Energy likes going from hot to cold. But remember, there's no such thing as cold. It's just lack of heat. But energy wants to go from hot to cold. Number 3, if two small beakers of water, one has a 70 degrees Celsius, and the other one is 80 degrees Celsius, and we sit there and we combine the two. So the two beakers are now combined, and we're wanting to know what the final temperature is. So again, guess what we're going back to? You're right, the 0th law of thermodynamics. You think this is important here? So we're going back to the 0th law of thermodynamics. If the two temperatures are combined, it wants to balance out. So what do you think the temperature is going to be? Yeah, you got it. Between the two temperatures. They're going to be between 70 and 80 degrees. And I meant to highlight, not mark that out. There we go. Okay. So the temperature has got to be somewhere between 70 and 80. Most likely it's going to hit right in the middle at 75. Number 4, energy transferred as heat always moves from object. So okay, again, we're going to energy transfer here. Heat flows from what to what? So we know heat is going to transfer, we just talked about it, hot to cold. So we have high temperature to low temperature. High temperature to low temperature, hot to cold. A little bit of tidbit of information, it also transfers from high kinetic energy. See if I can spell kinetic energy right. High kinetic energy to low kinetic energy. And that kind of makes sense, right? When things are hot, it's because you're moving and grooving. And then when you're cold, you're so cold you don't want to move. You're just like, can't move, so cold. So energy transfers to high energy, lots of movement, to low energy. Because the person who's not moving, you need to give them some energy so they can move. That's how you not freeze to death. So 5. Imagine you can observe an individual atom that that makes up a piece of matter, and that you observe the motion of that atom becoming more orderly. Orderly. So what's the opposite of order? Chaos. Man, y'all are so smart. Chaos. I cannot spell chaos. Nope, not spelling chaos. That's not happening, guys. Okay, chaos. So what word in our vocabulary goes with chaos? Entropy. Chaos, entropy go hand in hand. So, chaos, entropy. So which one can we assume in the system? So we're dealing with entropy, and it's becoming more orderly. So if entropy means chaos, and it's becoming more orderly, that means entropy is decreasing. Entropy is decreasing. Number 6. A chunk of ice with a mass of 1 kilogram at 0 degrees Celsius melts and absorbs that much energy of heat. So that's thermal energy. That is our cue right there. In the process, which best describes what happens to the system. So basically, you're adding heat to the system. You're adding thermal energy to the system. So let's go back to the ice cube thing. So when it's an ice cube, it's nice, solid, structured. It knows what it's doing. There's no movement really, just sitting there kind of vibrating a little bit, just very structured. When it starts to melt, you get a nice little puddle. It tries to stay together. It'll at least be together if you put it in a container, but if you just out on the table, it's just going to kind of go everywhere. So a little less structure, and then of course, when it evaporates, it just goes into little molecules everywhere, and it's bouncing off the walls, bouncing off your head, it's going everywhere. So it's going complete chaos. So as we go, we're going into chaos, or going into entropy. And why I can spell entropy over chaos? Mainly because it's right in front of my face. So it's going into entropy. So which best describes this system? So we're going from an ice cube to water. We're increasing entropy. There we go. A couple of math problems coming up. So let's, I know some of y'all don't like the guess method, but the guess method really does help you because it kind of breaks it down. So let's pull out our givens. So a crane can lift a 500 kilogram mass to a height of 30 meters in 2 minutes. The work done by the crane is, so again, let's pull out our givens. So we have this 5 kilogram mass. Oh, look, I was even nice enough to tell you what it was. Mass. So that's our M. And we want mass in kilograms, so we have no conversions needed. Then we have 3 meters. Oh, height of 3 meters. Man, I'm really nice. So we know our height is Y. And meters, we want meters. There we go. And then we have 2 minutes. I knew I was too nice. Do we like minutes? No, we like seconds. We have to convert the minutes to the seconds. So let's do that real quick. So we have 2 minutes. We don't want minutes. Minutes get shunned to the bottom. We want seconds. So for 1 minute, that's 60 seconds. So 2 times 60 gives you 120 seconds. So that is our little t. Dun, 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 dun. Now we're looking for work. So what work is done by the crane? Now remember, I will give you the formulas. You just have to remember what the letters mean and what units go with the letters or the variables. So the equation for work is work equals force times distance. So if we're looking at our givens, we have distance because d can be your y or your x. So d equals y or x. But, we don't have force. So now we have to go look for our force equation. So what's our force equation? Force equals mass times our acceleration is being lifted. So we know our acceleration is our acceleration due to gravity. And that's a constant. I will give you that, but it's good to know. So your acceleration due to gravity is 9.8. We have mass. That's part of our givens. So you end up going to do 500 times 9.8. And, we didn't write down our given of acceleration of 9.8. And that will be 4,900. It's force, so it's newtons. It's newtons. Then from that force, we can plug it into our work equation. Let's change colors. So our new force is 4,900. Doing calculations. And then our distance, which is y, is 30. So you times that by 30, and you get a really, really big number. And I've run out of space. Let me see here for a second. So I can get myself some more space. Maybe. There we go. More space. So our work ends up being 147,000 joules. Because remember, work is just a transfer of energy. If you want to put that into scientific notation, that'll be 1.47 times 10 to the 1. Get another color so we can jump and see it. A 1, a 2, a 3, a 4, a 5. So, be to the 5th joules. Now, that is a very important thing to know. So guess what I'm about to do? I'm about to put a yellow star by this one. So I would definitely know that if I were you. I'm going to give me some more room on this problem too. This problem again is the same thing, just this time it's asking for power. It's asking for power. So power equals work divided by time. We figured out our work. And time was given into the problem. Time was 2 minutes, but we converted it into 120 seconds. We plug that into our handy-dandy calculator. Maybe. There we go. And you get 1,225 watts. So remember, power is in watts. Pretty much everything else in this unit is joules. This is the one thing that's different. It's watts. And again, we can put that into scientific notation. Be 1.23 times 10 to the 123 watts. 1, 2, 3. So that is important to know, but is it yellow star important? Yeah, I think it's yellow star important. Put in yellow star by it. So while running, if you double your speed, your kinetic energy will, so you're doubling your speed. If you remember what your kinetic energy equation is, Ke equals 1/2 mass times velocity squared. Your velocity is squared. So if you're doubling your speed, and that's 2, so you have to square the 2. So that means it increases by a factor of 4. There we go. When doing a chin-up, a physics student lifts her 55 kilogram body a distance of 0.25 meters in 3 seconds. What is the power delivered by the student's biceps? Biceps. So you have to when you're doing chin-ups. You have to. So this one is very similar to 7 and 8. It's just combined. You have to sit there and find your force, then you have to sit there and find your work, and then you can sit there and find your power. So it's a 3-step. This one was very similar to your energy entrance ticket number 3. So yes, very similar. So again, let's get our givens. So we have the 55 kilograms, that is our mass. We have the 0.25 meters, that is your distance, and it's lifting up, so that's your y. And then the 3 seconds, that is your time. And remember, since it's lifting up, we always have the acceleration due to gravity, which is 9.8 meters per second squared. So again, it's just like that when we have to find the force first. So that's your mass times acceleration due to gravity. So 55 times 9.8. And then you have to do your work equals your force times your distance. In this case, it's y. And once you figure out your force, which is 539 newtons, you can plug that into your work equation. And you're going to multiply that by your distance, which is 0.25. And you get 134.75 joules. And then you can plug your work into your power. So you just divide that by your time, which is not very long. Curl-ups are hard. And so the power is 44.92 watts. Again, you can put that into scientific notation. You get 4.49 times 10 to the 1 watts. A couple of more multiple choice. Work is defined as, it's basically the definition of work. So it's your force times your distance, C. Power is defined as, again, that's just your power equation. So it's your work divided by time. Work is related to acceleration. And again, this is showing you that your force equals your mass times acceleration. So you can just plug that into your work equation, actually, because work makes you mad. Huh? Get it? Work makes you mad. Mass times acceleration times distance. Huh? Yeah, I know you're laughing. Just go with it. So, 14. If you lift one load up 2 stories, how much work do you do compared to lifting one load up only 1 story? So again, we're going with work. So work equals your force times your distance. So again, if you're doubling your distance, or in this case, you're decreasing by your distance by 1, you are actually going to compared to lifting 1, you're doing twice as much work, if I read the question correctly. If you lift 1 load twice, yes, it's twice as much work. I was making sure I didn't flip it in my head. So answer is C, because you're doubling your distance, so therefore you're doubling your work. A force does work on an object if a component of the force, so this key thing is, how does the force affect the object? So work only happens to the object if the force is parallel to the direction it's going. So if it's going to the right, the force either has to be going to the left or to the right, because it's parallel. If the object is being lifted up, the only force that can be affecting it's either got to be going up or got to be going down. So force has to be parallel to the distance. If it's perpendicular, it's not really affecting the distance. So if you're taking consideration of gravity of a box that's just sitting there, that gravity is not making it move or preventing it to move. So you have to think about it that way. Is the force trying to make it move or trying to slow it down, trying to prevent it from moving? Then there's work being done. If there's force on it and it's not affecting the movement, then the force isn't doing any work. One motor is more powerful than another motor because, so again, we have to look at our power equation. Our power equation is work divided by time. So how more powerful, that means over a time interval, the work is longer. So you want a shorter time, more work. That is your A answer there. In which of the following situations is negative work being done on an object? Negative work. That's when it's trying to slow down an object. So when you can think about when you push a brake against a car, you're driving, you push the brake, the car starts slowing down, your brake is doing negative work on the car. So in these examples, we need to see what's trying to be slowed down. So air exert a force on a parachute as the parachute slowly falls to earth. A rope exerts a force on a bucket as the bucket's being lowered down a well. Ice skater speed skates. And then a box is pushed across a frictionless floor. So the only one of those that's actually slowing down would be A, because without a parachute, that guy would just be falling. And that's bad. So the parachute slows you down. So the parachute's doing negative work because it's slowing you down. Let's see here. A box pushed at a net force of 200 newtons at a distance of 9 meters. What work is being done? We've done work equations before, so I'm just going to quickly do this. That's just force times distance. So that's 200 times 9. Pull out your handy-dandy calculator. I don't know why I did that. You can tell it's a long day when you pull out a calculator for that, because that's just 1,800. And I knew that as soon as I looked at it. Blah. So how much work is done in holding a 12 Newton sack of potatoes while waiting in line in the grocery store, and you're standing there for 5 minutes because Walmart makes you stand there forever. H-E-B is getting just as bad, though. So, but you sit there and you're just holding a sack of potatoes. How much work's being done? None. Zip. Zilch. Because think about it. The bag's not moving. So the object's got to be moving for work being done. Trust me, it's a pain in the butt. It's tiring to sit there and just hold something all day. But you're not doing any work physics related. Kind of thing about holding the big giant cat. Remember in the Kahoot? So you're holding the big cat. You're putting in some effort. You're not doing any work. Almost there. Almost done. Only 10 more to go. So 20. A 5-kilogram ball travels 12 meters in 6 seconds. It produces a power of 10 watts. What is the acceleration of the ball? I'm actually going to nix this question. This gets a little too complicated for what we are doing on the test, so we're just going to skip that one. 21. A system's initial internal energy is 27 joules. Then heat is added to the system. If the final thermal energy is 34 joules and the system does 26 joules of work, how much heat is added to the system? So now we're dealing with your internal energy. So you have delta U equals Q plus your work. So remember your delta U is your change in internal energy. So you have to do your final minus your initial. So you can break that apart. So I gave you an initial and I gave you a final. So it'd be 27 minus 34 equals, you're looking for Q plus 26. So your internal energy, I forgot to label my givens, for shame on me. I'm going to go back and do that real quick. And you're looking for heat. Heat is Q. So now you just do a little bit of manipulating so you can get Q by itself. The opposite of add is subtract. So you end up just subtracting that over. So Q ends up equaling 27 minus 34 minus 26. So you get a negative 33 joules. And remember that negative just means it's being taken out of the system, which I think that said that it's being added to the system. Yep. What happened mathematically? Oh, I flipped my final and my initial. I did my givens right on the thing, but I did not write it correctly in the formula. Y'all do that a lot. See, it happens. That would only be like a -1. Do apologize about that. See, I am human. I make mistakes. So that'll just be a positive 33. And see, that's another thing. It says how much should be added. So you knew it should have been positive because adding's positive, taking away is negative. And if you get a negative number, you're like, there's something wrong. So key points there. So I did that on purpose. I meant to do that. I wanted to show you how you can fix your work. I'm going to go with that. The internal energy of the gas in a gasoline engines decreases by 195 joules. If 52 joules of work is done by the gas, how much energy is transferred as heat? And then is it added so is it positive or is it negative? So this is asking you, is it positive or negative? And the internal energy is decreased by 195. So decreasing means it's negative. So again, you're using your change in internal energy equals thermal energy plus work. So that's your delta U equals Q plus W. So it decreases by 195. We're looking for Q. And it says how much work is being done is 52. So how much energy is transferred as heat? That is a lot of heat. That is a lot of heat being transferred. Because again, the opposite of adding is subtracting. And you're going to end up getting a negative 247 joules. And negative means it's being removed. So it's being removed. I'm going to yellow star this problem. So I definitely understand that system. 23. 23 is a roller coaster one. So we have the mass. And this one's a little bit more complicated because it's giving you an initial velocity. It's telling you what the velocity is. And then you have to fill out the chart. So this is just like 16 of your mixed calculations. And the only difference is in this case, we're giving you a velocity instead of just making it velocity at 0 at the beginning. So here you can figure out your potential energy using your PEG equals mass times acceleration due to gravity times y. You're going to plug that in for each of your heights. So you have height at 20, 20, 10, and 0. So you know the first two are going to be the same. So you can just do that once. So your mass of the roller coaster is 100 kilograms. Your mass should not change. No one should be jumping out of the cart. That would be bad. Your acceleration due to gravity is always 9.8 because we are on Earth. And then your height is 20 for the first one. Plug that into your calculator. And you get 19,600 joules. Now that's going to be the same for both times it's at the height 20. Now we can find out how much kinetic energy is happening by using your kinetic energy equation, which is 1/2 mass v squared. Mass does not change, it's still 100. In this case, our velocity is 2. So again, you just plug that into your handy-dandy calculator. Do not forget to squared. I was grading your entrance tickets, and I don't know how many people forgot to square the velocity. Please square the velocity. That's something very simple that a lot of people were messing up. So please, 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 please square the velocity. So in this case, your kinetic energy is 200 joules. Now, your total energy, there we go. It's not moving. I was like, I need more space. Your total energy equation is your mechanical energy equals your kinetic energy plus your potential energy. So remember, another word for total energy is just mechanical energy. So you just add the two. You just add your potential plus your kinetic, and you can get your total energy. So it's this horrible big gross number plus 200. And you get another horrible big gross number, 19,800. You know what's so cool about total energy or mechanical energy? It does not change. Does not change. So once you find one total energy, it's going to be the same all the way down. It's going to be the same all the way down. So then you just figure out the rest of your potential energy. So if it's 0, you know it's going to be 0. At height 10, it'll just be your mass times acceleration due to gravity times height. So it's 100 times 9.8 times 10. And you get 9,800. Once you figure out all your potential energies and you figured out all your total energies, you can figure out all your kinetic energies by using your kinetic energy equation. But again, you might forget to square that. What you could do, you could use your mechanical energy equation. And just subtract to find your kinetic energy. So what's going to end up happening is your kinetic energy equals mechanical energy minus your potential energy. So your mechanical energy does not change, and you're going to subtract that from each of your potential energies. Let me get back to my color here. That's just still. And then this all, since your potential energy is 0, all of your energy is kinetic energy. So your kinetic energy and your total energy end up being the same because you have no potential energy. And they have to add up to equal your total energy. Now, finding your velocity gets a little tricky because this is where you have to square root. That's another thing people forgot to do. People forgot to square root. So we're going to go back to the kinetic energy equation. And we want velocity by itself. We want to get velocity by itself. So you can manipulate the formula without even putting numbers in there. So we want 1/2 to be on the other side. So the opposite of 1/2 is 2. So we're going to multiply both sides by 2. And we get 2 times kinetic energy equals mass velocity squared. We want mass on the other side. So the opposite of multiply is divide. That's another thing a lot of people were doing. They were subtracting instead of dividing. So make sure you do the opposite. The opposite of multiply is divide. So you get 2 times kinetic energy divided by mass. And then to get rid of that squared, opposite of squared is square root. And what you do to one side, you got to do to the other. I think some of y'all were showing me that you were only square rooting the v squared and not your number. So you have to square root both sides. So your equation ends up being the square root of 2 times kinetic energy divided by your mass. And now you can just plug in numbers. So the first one is going to be the same. So it'll just be 2. And then the next one, our kinetic energy, is 10,000. We're going to times that by 2, divide that by our mass, which is 100, and then we're going to square root that puppy, because you don't want to forget to square root. And you get 14.14. And then we have that really big, lovely kinetic energy, because it's all the energy, because we're at the bottom. And when we have all the energy, it's moving the fastest, right? The most kinetic energy means you have the fastest part of the roller coaster. So we're going to times that by 2, divide it by our mass, and square root. And you can see that it is the fastest at the bottom of our roller coaster. So there's a couple of things in here I'm going to star. I'm definitely going to start knowing how to manipulate the formula so you can solve for velocity. You saw that on your entrance ticket. You will see that on your test. I'm also going to star your total energy formula, your mechanical energy formula. That is something I would understand. Your mechanical energy is made up of both kinetic energy and potential energy. So it's your mechanical is potential plus kinetic. That goes hand in hand. And if you notice, so at the very end of this roller coaster, it goes really, really high. Just on its own, could it make it past where it started? The answer is no, it cannot. It cannot go past where it started. If it started at 20 meters, it cannot go above 20 meters without any help, because that's the max total energy. We have 19,800 joules of total energy. We cannot go above that. So going higher than that means we're going above that. So let's say I made you look at a roller coaster picture and decide if it would work or not. Hint, hint. Okay. Cannot go above the starting height. And so that's a star, but that's not a question on here. That's just me adding things, throwing things at you. That's very important. So the last couple of questions is just matching, knowing what convection, conduction, and radiation are. So which transfers heat through direct contact? That will be your conduction. Through fluid motion, that is your convection. And then through waves is your radiation. So a couple examples is radiation could be like a fire or the sun. Convection is like boiling water or your convection oven. And then direct contact would be like you touching the stove before it cools down and you're burning yourself. Direct contact. Or you're really cold and your best friend's warm, so you snuggle up next to him. Direct contact. So you have to be directly touching. Now, an object can have multiple things. It can be radiation and convection. In theory, it could be radiation and conduction. I don't think that'd be very good, but it could technically thing. So you can have multiple heat transfers happening at once. Hint, hint. So I would know that if I were you. The last matching is our laws of thermodynamics. So energy is neither created nor destroyed. Energy lost to one location is gained somewhere else. So that is the first law of thermodynamics. Total disorder of a system, that is your second law of thermodynamics. When two objects are in contact, the heat flow goes from high to low until it's in equilibrium. That is your zeroth law. And then absolute zero is your third law. That's officially done with the review. A couple of things that I wanted to touch on that might have not been very clear in the review is, let's say here, energy is always transferred. It's always transferred. And we talked about the car. Let's go back to the car example. You slam on the brakes, it slows down, and friction is causing that. Do not do it, but I'm sure you've known someone that has like burned rubber. You get your tires going and stuff, and you actually have that burned rubber smell, and it's because friction causes thermal energy. Just rub your hands together. You rubbing your hands together, you can feel warmth. So friction causes heat. So I would definitely know that. If an object, friction is happening, your energy is being transferred into thermal energy or heat. That's something definitely I would know. Another hint, dealing with your work equation. If you have multiple things like stacked on top of each other, you have to add your masses. So if you have a box on top of a box and you're pushing the bottom box and the second box is coming with it, you have to add both of your masses. So I would definitely know that. The only other thing that I think I would know is remember your equation, your potential at the top equals your kinetic at the bottom. We kind of touched on that dealing with the roller coaster. So as long as it is not moving, like in our example here, you can see it's moving. So that doesn't quite work. But if the object's not moving at the top, and you're trying to find your kinetic energy, you can use your potential, gravitational potential energy, or vice versa. So I would definitely know that your potential at the top equals your kinetic at the bottom. And here, I'll do an example for y'all real quick. And this will be my last example. So going back to the problem you had on your energy, Schoology work, when you had the person swinging from the vine. So you had you were given you were trying to find the height. So you were looking for height, and you were given the velocity. So let's just say the velocity is 12 meters per second. So the person's running towards the vine, jumps on the vine, and swings up. So running towards the vine, jumps on the vine, and the person swings up. And we're trying to find how high the person went. And we know the velocity, how fast the person was going at the bottom, but we're trying to find height. So that's when you can do your potential at the top equals your kinetic at the bottom. So you end up doing your mass times acceleration due to gravity times height equals your 1/2 mass v squared. Does the mass of the object change? No. Good. So that means you can just cancel out your masses. Masses is not needed. So you have your acceleration due to gravity, which is 9.8. You're looking for your y equals 1/2, and you have your velocity. Do not forget to square it. Okay. Just want to make sure you all knew that. The opposite of multiply is divide. Opposite of multiply is divide. So you want y by itself, so you divide your 9.8 over. So you get 1/2 times 12 squared divided by 9.8. You plug that into your handy-dandy calculator, and you get 7.34 meters. There we go. So that's it for the review. I will slowly scroll up just in case you missed something, or, you could, rewind the review and rewatch it if you want. Hopefully that helped. If you have any questions, you can always message Ms. Verona or Ms. Heath, or message through Schoology. Hopefully you have a wonderful day. Happy studying. Bye.